Let's solve this problem. A 50-meter rope with a mass density of 0.2 kilograms per meter hangs over the edge of a 30-meter building. How much work is done pulling the rope to the top? All right, so let's make a sketch. Let that be the building. And then suppose this is the rope. We're just going to imagine that it's parallel to the building, but without any friction. We have a 50-meter rope, but only a 30-meter building. So that means that about 20 meters, or exactly 20 meters, is on the ground. The main idea here is that work is force times displacement. But what makes this problem challenging is that not every part of the rope is going to get displaced the same way. Let me subdivide this rope into little pieces. The piece at the top will hardly get displaced at all, but the pieces on the ground are going to get lifted 30 meters. So what we're going to do is consider this rope in two parts. The first part will be the part that's hanging, and the second part will be the part on the ground. Okay, let's start with part one. And the first thing I'm going to do is assign a coordinate system to my picture here. So let's have x equals 0 be the top of the building and x equals 30 be the bottom. You could do that differently. So you could flip those if you'd like, but I think it's easier this way. Consider this piece of rope. The force acting on this piece. From Newton's second law, we'll think of that as the mass of that piece times the acceleration downwards due to gravity. The mass of the piece is its length times its mass density. So we'll say that the length of this piece is delta x because I've chopped it vertically into little segments. So it's delta x, and that unit is meters, times 0.2, where the unit is kilograms per meter, times 9.8 meters per second squared. As expected, the overall unit here is kilogram meter per second squared, or in other words, it's newtons. So that we can write this as 1.96 delta x newtons. The way I've chopped this up, the top of the segment and the bottom of the segment are also displaced a little bit differently, analogous to the entire rope. However, what we want to imagine is that I chop finer and finer, so that overall, this entire segment's displacement can be thought of as equivalent to the top of the segment's displacement. Given that my coordinate system measures down from x equals 0, the displacement of this coordinate is x. So like if this is x equals 3, we go up 3 meters. So the displacement for that little piece of rope is x meters, where x represents the coordinate position of the top of that little piece. So that overall, the work done lifting this rope is going to be the sum of the work done lifting the first part and the work done lifting the second part. Let me jump right to the integral that we need for part one. Force times displacement across the first part of the rope is going to be the integral of 1.96x dx. So you can think of this integrand as the product of force and displacement. From x equals 0 to x equals 30, that's at the bottom of the building. So this is part one. To that, we will add the part two work. This piece of rope is all on the ground, which means that all of it gets displaced 30 meters. We no longer have this varying displacement. So it's going to be the length of this rope, that's 20 meters, times the mass density of 0.2 kilograms per meter, times the gravitational constant, times just 30 meters. So there's no integral here because there's no varying condition. This is part two. I'll let you integrate this on your own. That's a very straightforward integral. And just tell you that at this point, when you add these two together, you should get 2,058 joules. I hope this demonstration helps you lift ropes, chains, and bags of sand to the tops of buildings.